Welcome to Chapter 9. Today we're going to talk about special stains on neural tissue. Now before we get started, I'd first like to congratulate you on getting halfway through our special staining material and over halfway through the overall material that you will need to pass the HT or HTL exam. And before we get started with the actual stains today, I'd like to just recap some things to look at when you're studying. So especially when it comes to special stains, it can be really hard to take in all of the information that's contained in your text and put it in any kind of logical order, because you don't want to just memorize the steps and the reagents like it's a cookbook. You don't want to just know them, you want to understand them. You want to know why you're using a certain reagent at a certain step. So I just went over, I thought about some ways that I studied, and hopefully this helps you out. So when you're looking at a special stain, you'll notice that thus far, there's a lot of mechanisms, and a lot of those mechanisms are common between different stains. So a mechanism might be using a metal mordant to adhere a dye to something, and then using excess mordant to differentiate that, like in our elastic stain. And so knowing what the mechanisms are and just kind of recognizing how they work can really be helpful in making that information less arbitrary and making those steps make a little bit more sense. So knowing the mechanisms, I think, is kind of the foundation. If you know the mechanisms, knowing all of the stains that use them is going to make a lot more sense. So next, I would look at staining patterns. And this is less about memory and more about importance when it comes to taking the exam. So staining patterns can be really low-hanging fruit, kind of like one of your first questions or first level questions that you'll see is, here's the stain, and it might not even be a picture, it might just be a sentence. It'll say, here's a stain, and what color does this substance stain? So just knowing those, being able to memorize those, is going to take you really far on the exam, just because it's easy material to draw from. So make sure you know your staining patterns. Don't just know that this stain stains for this tissue. You have to know within that stain what stains what. So whether that's looking at pictures or just reading over the procedure a lot, make sure that you have that down, because that's going to be very, very important when you take the exam. Once again, if you know what the mechanism is, then knowing how the staining pattern might be is going to make a lot more sense. Next, you want to look at special techniques. So within a mechanism, so if you're looking at something like silver stains, so we have a lot of silver stains. We've talked about a few already, and we have a few more to come. So just knowing that something is a silver stain doesn't really tell you that much as to why there's a bunch of them. So knowing what the special techniques are within those silver stains and why you have all the different ones can really help. So knowing that something is a silver stain initially is good, but being able to know why this silver stain is special compared to the rest is kind of the next step. So once you know the mechanism, kind of know the staining pattern, then you want to know what makes it special. Why use this specific technique to get this staining pattern? Next, you want to look at usage. Usage is, for me, kind of a way of applying that knowledge. So at the mechanism level, it's kind of knowledge and comprehension, which is kind of our first and second levels of understanding things, or first and second level of learning. At our third level, that's application. So once you're able to apply information, then not only does that demonstrate that you really know what you're doing, but it also means that you have all of the prerequisites. You have knowledge, you have comprehension. So when we get to usage, you want to be able to take what you know about mechanisms, staining patterns, and all the special techniques there, and say, why would a pathologist order this? And that does a couple of things. Besides reaffirming that you know what you're doing and know the background knowledge, it also makes it a little bit more interesting. So maybe you're looking at flashcards, and flashcards by themselves can get really boring and really mechanical, but usage kind of takes you out of that and puts you into the spot of a pathologist to say, all right, this is the disease process. What would you order on this? So the way that I would study usage is to just search for the stain and usage. Just Google it. You can see a bunch of stuff from pathologists and some stuff from histology technicians. They'll tell you common stains to use on different kind of disease processes, and try to find color plates. Find actual examples where they said, okay, this disease process because we found this constituent, and we can tell because of the special stain that this constituent is in this state. So it's really about taking all that knowledge that you had in these other steps and making it kind of useful in the real world. So once you get through all this, then honestly you get to the hard part, which is reagents. Reagents can be really difficult to learn, because when you learn them initially they look arbitrary. I mean, when I started histo school, I had a background in chemistry, and still a lot of our reagents were pretty foreign to me, pretty arbitrary, because there's a lot of chemicals that you can work with, and you're most likely have not encountered all of them by the time you get into school. So you're looking at a list, and it's just step 1, step 2, some chemical, step 3, some other chemical I don't know. And if you just learn it like this, then these reagents aren't going to mean anything to you. So that's the reason why I put this kind of after everything else. If you know what the mechanism is, and you know the staining pattern should be, you know the special techniques and the usage, chances are when you look at your first chemical, let's say, you'll say, okay, this chemical does this because this is the mechanism we're using. So that's why we do this chemical first. So you kind of want to make the transition from these all being arbitrary to being in a logical order, so that when you look at the whole procedure, you say, oh yes, this procedure makes sense. We would use this reagent first, this reagent second, and this one, because the mechanism that we're using is this, and we're trying to get this kind of staining pattern, and within that we're using this special technique. So of course we would use this chemical. Now this would require you to typically look outside of your textbook a little bit if you really want to understand the chemistry behind it, but I really recommend that. And maybe don't do that on your own if that's a really tall order for you. Talk to your techs, talk to any instructors that you have. If you're one of my trainees, then absolutely come to me. I will, if I don't know outright, because it is pretty in-depth information, I will certainly find it for you. But the goal here is to make sure that this is not just a mystery list. We can't have that, because you're not going to remember them. Or if you do, then you're going to forget them very quickly. And there's a lot of reagents and a lot of stains to know. So when it comes to test day, I don't want you to have to rely on kind of that short-term, really arbitrary memory. I want these to make sense. You want them to be in some sort of logical order. And last, once you really know everything, you practice. Practice can look like a lot of things. Practice might be you actually doing the stains in a lab. Practice can be going through some sort of simulator and just putting things in order, and knowing that if you were doing it in the lab, that you would know what to put when, and you know the order of things. And just kind of going through those paces and saying, okay, this is the reagent I would need now. I know that because they have the distinct order. There's a reason why we would use this thing next. Kind of just cements the whole thing. And then that repetition becomes something that is less just a flashcard and more of a practice of applying that knowledge. So, all in all, the whole goal here is to take something that seems very arbitrary, maybe doesn't make a whole lot of sense, so that being a whole procedure and the principles and mechanisms behind it, and breaking it down so the whole thing makes sense to you. So when you take the exam and you see a question like, this stain looks like this, what went wrong? You can look at it and say, oh, well, okay, I know what the mechanism is for that. I know what the staining pattern should be. It looks different. I know the special techniques we use, and we know why we use it, and I know what the reagents are and what order they should be in. So you can look at the stain and say, oh, somebody left something out, or somebody didn't differentiate enough, or whatever. But without having all that background knowledge and really having a tight understanding of all of it, this won't make any sense. You might get lucky. You might see something that's similar to a test bank question. And more than likely, you're going to find something that really requires you to actually understand and not just memorize the information. So, with that being said, let's start our first stain. That is going to be Cresselect's Violet. And Cresselect's Violet is going to be used to demonstrate Nissl Substance. So you're going to see that around the nucleus and the cell body of a neuron. Now, something you're going to notice with a lot of our neural stains is that the thickness is going to be pretty important. I'm going to try and note these when I can, but really you should be following whatever the procedure is in your laboratory. So Cresselect's Violet, according to my textbook, is to be cut at 6.5 or 6.628 microns, and that just depends on the thickness of the tissue that you're trying to achieve. And it could be that maybe cutting something in half, like a neuron, could release the Nissl substance. That kind of stuff is not entirely sure to me, but I would assume that's probably what's going on here. So with this stain, what we're going to do is essentially stain everything with Cresselect's Violet, which is a basic dye. It's going to stain the Nissl substance, which is basophilic, as well as nuclei. And so the balance that we have to strike here is we want to make sure that we show the Nissl substance, but also be able to see, contrast that with everything else in the background. So a lot of times what you use for a control for this is spinal cord, which luckily with neurons, you're not going to see nuclei kind of bunched together if you cut it at the correct thickness. So it's not as big of a deal as you might think if you're going to try to find something else as basic and amongst other other basophilic constituents. But we are going to use a little technique here to kind of to add that contrast. Because the Nissl substance is going to show up fairly dark just because of how thick it is compared to the nuclei, we're going to use a way of kind of decoloring this. So it's sort of a regressive stain in that way. So procedurally wise, we are going to stain everything with Cresselect's Violet, and that's going to be pretty close to like hematoxylin purple, really. So yeah, something like that. And once we stain everything, we're going to rinse that in distilled water, and then we're going to place them in 95% alcohol, and then we're going to put them into xylene. Now we're going to do something interesting with this. We're going to put them into a xylene balsam mixture, and this is going to be kind of our differentiation step comes after this. Now, as far as why using balsam, my guess is to protect the Nissl substance. So for some reason, using balsam can be a bit more gentle than other reagents, and it might kind of give it an action of protecting it from differentiation. So that might differentiate other things more. So the surrounding nuclei might fade out just a bit compared to the Nissl substance. I'm not entirely sure on that, but that would be my guess. So what we're going to do is going to put the whole section in the balsam xylene, and then we're going to differentiate in absolute, and we're just going to keep putting it through absolute and then checking it, and then putting it through xylene. So it's going to be something like, it's going to look, let's say we have a bunch of Nissl substance here, and we have some surrounding nuclei. Like I said, it shouldn't be terribly dense because neural tissue, so that's kind of good. So let's say we had just one neuron with a bunch of Nissl substance in the middle here. What this should do as you go differentiate is you're also going to see a ton of background staining just in general. So the nuclei here are going to stand out, and then you're also going to have a bunch of kind of this like background staining, which makes it so that the nuclei and the Nissl substance don't really stand out that much. And what the differentiation is going to do is kind of get rid of that background. So as you differentiate it, you're going to see the background just kind of fade out until eventually, in this method, you're still going to have some. It's not going to be completely clear, but it's going to be pretty good. You're going to be able to see the Nissl substance and the nuclei. And the chances are when you do this differentiation, it's kind of hard to control. Also, you can't really see it macroscopically, so you have to check it microscopically after you're kind of done with it. So it's kind of hard to look at the slide and say, oh, okay, we're done differentiating. So you want to do the dips in alcohol, put it through xylene, and then check under the scope. If it's not differentiated enough, then you got to put it back into the balsam xylene, differentiate it in alcohol, put it through xylene again. And just keep doing that until you have a pretty good contrast where you see the nuclei and your Nissl substance. So this can be kind of a pain. This thing can be sort of hard and time consuming, depending on how many times you have to go through those steps. But eventually you should end up with something like this, where you can tell where the Nissl substance is, and you can see the nuclei as well without a ton of background stain. So now that we have the first method, there's a second method, which I think is a lot easier, and that is one where we actually acidify our crystallized violet solution. And what that does is it allows us to just stain and dehydrate and put it in xylene. Now, the trade-off there is, well, kind of good on one end because we are able to get rid of the background for the most part. I mean, it's pretty well gone, though we also get rid of some of the staining overall, and the Nissl substance can be kind of faded out. So it's a shorter method that way, a lot less frustrating, but you get less intense staining on your Nissl substance and the surrounding nuclei. So that's the trade-off that you're looking at there. So that's your second method, and once again, it's a lot easier, but there is that trade-off. The next stain that we're going to look at is the Bodian method. And the Bodian method is a silver technique that we are going to use to stain nerve fibers. And so, like I said before, we're going to have some silver techniques to do special things, and you're going to want to remember what makes them different. In this case, we're going to use an impregnating solution called protargol, which is a silver protonate, so basically silver, that's going to attach to everything if we didn't add anything to it, which would be a huge mess. So your connective tissue fibers, basement membranes, as well as your nerve fibers would all stain with this. And so what we do is we kind of edit that a little bit by adding copper. And what copper does is it replaces the silver that's deposited on the connective tissue fibers. So it kind of competes with the silver and pushes it out. So at that point, you're going to have silver in kind of all over the place, but it is depositing specifically on the nerve fibers. So as far as procedure goes, you're going to prepare that solution. So it's going to be protargol with some clean copper put into it, and you'll let that sit overnight. And what that'll do is it's going to turn everything kind of a gray color, just kind of, as we see with silver techniques. It's going to turn everything kind of a gray, and you might see nerve fibers start to show up a little bit. But we haven't reduced anything, so it's just kind of, you couldn't use this diagnostically. You might see some, and even if that, it's going to be very, very faint. So it's not all that useful yet. But now that everything's kind of deposited, then we're going to reduce them. And in this case, we're going to use hydroquinone to reduce our silver. Why are we using hydroquinone and not something like formalin? That just happens to be what we do in this specific procedure. Other folks have used things like formalin and with the hydroquinone. But so specifically for the Bodiam method, we're going to use hydroquinone to reduce our silver. And at that point, it should start to actually deposit. But remember, when it deposits, it's still not all that visible. It can be kind of even an orangish color sometimes, or a brown when it's there, and it doesn't have a ton of contrast. But you might see some neurofibers start to show up. So at this point, at the reduction, it's there, but we haven't toned it yet. So we just kind of have some squiggles, and they're not going to have a ton of contrast when we add a counter stain to it. So we have to add another step to this, which is what we're used to. We're going to use gold chloride, and gold chloride is going to actually replace everything. So gold's going to make everything very, very dark. Well, the things that we want to be dark, at least. So you're going to start seeing actual lines start to show up at this point. And after the gold chloride, then we will continue to develop in an oxalic acid. And so we just wanted you to do that until the contrast is really good. So that should get rid of some of the gray in the background. There's still going to be some, but you just keep doing that until you're seeing some really good development of the nerves and maybe a little bit less background staining. And what you should see is just what we're looking for is just nerve fibers at this point. So we've toned everything, we've developed, and next we're going to use our sodium thiosulfate to get rid of any of the extraneous silver that hasn't been reduced. And that'll also kind of clean this up. So you might have some dots here initially, and that sodium thiosulfate is just going to get rid of that, as well as some of the background too. And then after that, you're going to use a counter stain. So in this case, we're using aniline blue, which ends up being something along those lines. And there you go. That's your Bodiam method. So you're using silver impregnation with protargol, and we're using copper to get rid of anything on the connective tissue. Then we're using hydroquinone to reduce everything, gold chloride to tone, and then oxalic acid to develop it further, and finally that sodium thiosulfate to get rid of all the extraneous stuff, and then counter stain as needed. In this case, we used aniline blue. And that's your Bodiam method. So our next technique is the Holmes silver nitrate technique. This one we're going to cut sections at 10 to 15 microns. This one is also for nerve fibers and neurofibrils. The difference with this one is, for one, we're going to use cerebral cortex. So because the spinal cord is going to have a bunch of axons kind of in the way, and it's going to be hard to tell what's what. So cerebral cortex tends to have some branching patterns that are fairly uniform, so you can tell whether it's working or not. And this is meant to be kind of an improvement upon the Bodiam method. So the Holmes method uses a buffered impregnation technique where we're using our silver nitrate like we normally do, except we're going to buffer that with pyridine, and that's going to make it so that the impregnation is done at a high pH. And we think that for some reason that's going to change how the metals are picked up, and it might be a bit more consistent from one stain to the other. So apparently with Bodiam methods, And I say apparently because I don't have that much personal experience with them in the lab, but apparently it can be kind of inconsistent. So the Holmes method is supposed to be just a bit more specific. So with Holmes method, we are going to put our slides into just regular old silver nitrate at first. So you might get some gray on the slide at first. You're not going to see a lot of differentiation between things. It's just sitting in silver nitrate. Hopefully you don't see too much here, because if you get something that's really dark, like if it starts looking like this, then chances are you have contamination in your glassware. So that's something to keep in mind, is that any kind of silver method, you gotta make sure you clean that glassware with some sort of acid, nitric acid, or sometimes sulfuric or hydrochloric can be enough to clean that up for you. But right now, at this point, we have just a little bit of gray there, maybe. Hopefully not too much. Then after that, we're going to wash that off to get the excess off, and then put it into our impregnating solution. We're going to let that incubate overnight. And then you're going to take that out, shake it off. You're not going to see a whole lot of difference here, really. You might see like a few lines here and there at this point. So let's just say you see a few neurofibrils here, but really not a whole lot. Then we're going to tone it with our gold chloride. So you might see a few show up just a bit more darkly, but really in this one, it says that you're not going to see a ton. You're not going to see a ton show up quite at this point. It's really not until we get to the next step, which is when we put it into oxalic acid, and that's going to really do the development part. And the range for this one, as far as time goes, really depends on how well it develops. So you really just want to watch the slide, either macroscopically or microscopically, and you want to tell when they're the neurofibrils are kind of a blue-black. So I'm just going to, it might be something like this color, and you're essentially just watching them to see when they're done developing. And when they're done, then you take it out. And then you're going to wash that off, and you're going to use silver nitrate to get rid of any of the stragglers, the unreduced silver, to kind of clean this up. But essentially, you should be able to see all the fibrils after that, and it should be really clean. And you might actually see some unstained spaces around the neural bodies, but we're really looking at neurofibrils here, so that space isn't actually supposed to be there, but it's more artifactual with this. So you might see it's kind of an open space here, but you should be able to see all these fibrils. They should be nicely differentiated, and the background is just going to stay this kind of gray color. Our next stain is the Bielchowski PAS stain. So the Bielchowski takes what we learned with the previous stain, so our Holmes method, where we use kind of a basic environment to be a bit more selective, and we use this one specifically to find neurofibrillary tangles associated with Alzheimer's disease, and as well as adding the PAS there to highlight some of the amyloid plaques. So this is kind of a stain used to identify Alzheimer's disease. So the way we do the Bielchowski part is, when we're going to do that first, is we're going to put our slides into ammoniacal silver. So kind of like in our previous method, where we kind of put it in the silver first, kind of let it soak in some of the silver, and then we are going to remove that, wash it off, and then we're going to put it in an ammoniacal silver solution this time. And so that's something we're used to with our other silver methods. And then we're going to wash them in ammonia water. Now, while those slides are sitting over here in our ammonia water, that previous one we had with the silver nitrate, or the ammoniacal silver, now we are going to add our developer to that. So, as you can imagine, that's going to make things very, very dirty, especially on the slide. So, yeah, so it's sitting over here in your ammonia water solution. you're going to add the developer to this, and then you're going to transfer your slide back over here, and it's just going to get just all kinds of, it's going to look very, very dirty looking. It's going to be very brown. Then we're going to wash that again in ammonia water. I'm not even going to try drawing this because it's just, it's real messy at this point. Then we're going to tone it. So as we know, when we put things in gold chloride, the gold replaces all of the silver that's attached to the tissue. And so it's going to turn gray. So at that point, we're going to see things going to be kind of gray all over. And you're going to see your fibers and your entanglements are going to start showing up. And then you're going to put that in ammonia water again, and then use sodium thiosulfate to get rid of any particulates kind of floating around in there. A lot of times you're still going to have kind of a gray background to this. It's hard to get rid of all of it, but it should be fairly faint. It should be faint enough that you can tell the fibers from everything else. Then we get on to the PAS part, which we're familiar with. So we're going to put our slide into periodic acid, put in our shift reagent, and then at that point, all of our amyloid plaques are going to show up. So might look a little something like that. And so as you can see, we have our neurofibrillary tangle with the amyloid plaque surrounding it. And that's your Bill-Chomsky PAS. So we're kind of combining what we learned from Holmes, adding a PAS. That way we get the amyloid plaque and neurofibrillary tangles, both associated with Alzheimer's, all in one slide. So for our next stain, we're going to use a modification of the Bill-Chomsky method, and it's called the Sevier-Munger, or maybe Sevier-Munger, I'm not sure. But if you see Sevier-Munger, then you'll note that it is a modified Bill-Chomsky. And in this method, we're actually going to take out any kind of toning. So the background's going to be really, really yellow. So we're not going to replace our silver with gold, which is going to be silver. And we're going to kind of leave that, that background there. The reason for this hasn't been explained to me all that well. My guess is that because this is known to be a very reliable method and it's fairly short, that might be why we favor that. So essentially what you do here is you put your slides into silver nitrate, and then we do like we did before, where we add our developer to our ammoniacal silver. And so they're actually going to let the slides develop in there and just have to keep checking them. So you're going to have what's going to end up being kind of a golden yellow background. Maybe a bit more towards yellow. Something like this. And it's going to vary in terms of how close to orange it gets. But essentially you're going to have that with your neurofibers and the tangles are going to show up. And essentially you're just going to use sodium thiosulfate like you normally would to get rid of any excess, but you're going to keep this background here. So our next stain is 5-flavin S, and we're going to cut that at 6 microns. And this is a fluorescent technique, so that's why our field here is dark. This staining technique is actually super specific for what we're looking for. It's actually supposed to be more specific and possibly cheaper than any of the other methods that we talked about when you're trying to find neurofibrillary tangles and senile plaques. So in this method, we are going to pre-treat our slides before we put the 5-flavin S on them. We're going to treat them with some potassium permanganate and sodium hydroxide. And what this is going to start to do is get rid of any kind of autofluorescence associated with lipids, which in neural tissue, there's a lot of lipids. So we want to just get rid of the autofluorescent properties of those by pre-treating them. So the first thing we'll do is deparaffinize and bring everything down to distilled water, and then we're going to rinse those with water, and then we're going to cover the slides with potassium permanganate. Wash that off, put it in potassium metabisulfite, oxalic acid, and agitate. So when we're doing this technique, there's a lot of agitation going on. We're going to wash that off, put it in sodium hydroxide peroxide, wash that off, do a final rinse with filtered water, with millipore filtered water. And we're going to put the slides into acetic acid, wash that off, put them into alcohol for a couple changes, and then place them into the 5-flavin-S, and that's going to be on a shaker for about 7 minutes. Now, of course, we're not going to see anything on the slide at this point. This is a fluorescent technique, so don't expect to see really anything on your actual section just by looking at it. But then we're going to rinse the slides with a couple of changes of 50% alcohol. We're going to keep the agitation up for this. Go through 95s and dehydrate down to xylene, and make sure you mount with something that's a non-fluorescent medium. And when it's all done, when you look at it under a fluorescent scope with a proper filter, all the neurofibrillary fibers are going to show up. So you're going to see a lot of these in the background. And then when you see the plaques, so the tangles and everything, they're going to show up, and maybe not quite that vibrant. They look a little like that. And so you'll see the senile plaques and just these big convergences of all these neurofibrillary fibers that'll kind of be so tangled that they look like just a blob of material on the scope. And that's 5-flavin-S. So to remember this one, it's the most acidic out of all of them, and it's supposedly low cost. Our next stain is the Mallory PTAH, or phosphotungstic acid hematoxylin technique. This technique is going to be used to show glial fibers, and you're going to cut it at 6 to 8 microns. The mechanism behind this is essentially we're going to use phosphotungstic acid as a staining solution. And so if there's any kind of hematin around, it makes a blue lake. And this that makes the blue color for the glia and some of the myelin. And that's where one of the limitations of this stain come up, is that the myelin and the glia can kind of be the same color, so they're hard to differentiate. But the neurons, so the cell bodies, are going to be kind of a salmon color. In order to do this, we are going to make up our PTAH, so that's hematoxylin, phosphotungstic acid, so we can get that lake. And we're going to mortar our sections in Zenker with acetic acid. So once we take them out of the Zenker, we're going to wash them and then put them into Lugol iodine. And there's a note here to make sure that we don't put them through sodium thiosulfate because that could impair staining later on. So we're going to decolorize those. So once you put them in Lugol iodine, they're going to be pretty dark. You want to decolorize them in some 9,5 alcohol, rinse rapidly, and then put them into potassium permanganate. Then we're going to wash that off. We're going to decolorize them in oxalic acid, and then we're going to stain them in the PTAH at this point. So this whole thing up until this point was essentially getting them ready to accept the PTAH. And after that, everything should look as though the glial fibers are going to be blue. So if you have any kind of glial fibers, which will typically run next to your actual axons, those will be blue, as will myelin, will also be a blue color. So you see a lot of these of varying widths, because it's kind of all those fibers are the same color. And then when you're looking at the neurons themselves, they'll be a salmon color. So let's see if I can get close. So something like that will be the actual neuron cell bodies. So the notes for this do say that it's not great because of the lack of differentiation between the two. The Holzer method, which we're going to cover next, is thought to be better, but even then, with modern IHC techniques, both of these methods have been relatively replaced. So if your lab has some more advanced IHC menus, then you're probably not even going to see this, but we still have to note for the exam. Our next name, as I mentioned, is going to be the Holzer method. This method allows us to see our glial fibers, and we are cutting at 6 to 8 microns again. So this case is supposed to be a bit more specific than our last method. And in this case, what we're going to do is we're going to use some fairly toxic chemicals to make this happen, and that's kind of one of the drawbacks here. But let me take you through this. We are going to put our sections into phospholipid acid, alcohol, drain that off, and then cover the sections with absolute alcohol chloroform. So at this point, we know we're working with some pretty hazardous stuff. Everything has to be done in a hood. This mixture is going to make them translucent. So you're really not going to see a whole lot on the slide at this point. But what that does do, as far as I can tell, the mechanics on this are a bit fuzzy, but as far as I can tell, the chloroform is going to allow our next reagent, which is our crystal violet, to infiltrate the glial fibers and everything else on the slide. So anything else that would take in crystal violet is also going to be kind of a deep blue to purple. And at this point, everything on the slide is just blue and purple. And we're going to replace our stain with 10% potassium bromide. And as far as I can tell, this is going to halt our stain at that point. So you're just going to have a whole lot of blue on this slide at this point, and then we're going to let blot this dry. So we've stopped the reaction, but we're not done because everything's blue. We can't tell what's what. Once everything is actually dry, then we're going to differentiate. And our differentiating solution has chloroform and aniline oil, both of which are pretty dangerous. The thresholds for exposure are very low. Everything has to be done in a hood. So you have to be super careful when you do this. But when you're all done, all of your glial fibers should show up as kind of a deep blue color. And it's more selective than our last one. So that's why you might take the risk with those hazardous chemicals. But like I said before, IHCs are really kind of replacing these methods, thankfully, because it seems pretty dangerous. I've never done a Holzer stain myself, so I'm really relying on the reference material here. But this doesn't sound like something I would want to do on a routine basis. And while it does work, I really want to be in the lab with chloroform and aniline oil for any extended amount of time. So yeah, that's our Holzer method. So for our next stain, we have another pretty dangerous one that's been luckily mostly replaced by immunohistochemical stains. But this is the Cahal method. So in this method, we are going to use frozen tissue. So we're going to cut that at 20 to 30 microns. So it's pretty thick. To get astrocytes, that would be my guess is why that is so thick, is they can be fairly thick pieces, functional pieces. So probably to try to make sure we don't cut through it and stop it from having its absorptive properties, which is what we're going to rely on here. So we cut it, and then we're going to fix it in formalin ammonium bromide for at least 2 days, but no more than 25 days. So as you can tell, this probably isn't a very speedy method of seeing these astrocytes, but apparently it works. The formalin ammonium bromide, cut, frozen, and put into distilled water. So it's not going to hit a slide yet. You're going to transfer those into the gold supplement solution. Okay, so we're going to put that in the dark for about 4 hours. So the gold supplement is gold, so gold chloride with mercury chloride. So the mercury there is what makes this really dangerous. So you have gold and mercury, and for some reason, the mechanisms behind this are not known to me. The literature that mentions any of it is behind a paywall, so I'm not actually able to elucidate this mechanism completely, but we know that it works. So essentially, the astrocytes are going to take up gold and or mercury. We know that the mixture has to be correct. They have to be even. So for whatever reason, astrocytes will take up gold and mercury, and it'll turn them purple and eventually turn them black. So after they've been sitting in the supplement, we're going to wash those off and then treat them with sodium thiosulfate to get rid of any of the extra. So sodium thiosulfate, once again, getting rid of extra metals. And then we're going to mount them and on an actual slide at this point. So the whole time these have not been on a slide. So now that's all done, put it on a slide, blot it with paper, and dehydrate and mount it with a cover slip. So by the end of this whole thing, you're just going to see your astrocytes here. I'm probably not going to draw them very well, but the point is that we need to be able to see these tendrils coming off of our astrocytes. And the background can be kind of a pink color, so purple to pink, as I understand. Once again, these things are not run very often in the labs where I have worked, and my guess is just because they've been replaced by IHCs for the most part. But yeah, you might see something like this. And so if you see kind of that pink to purple background, and you're seeing some very, very dark lines that look like neurons and look like axon or astrocytes, and you're seeing those little projections, and chances are that's a Cahal using gold supplement. Next up is our wheel stain, and our wheel stain is going to allow us to show myelin sheaths. This one's going to be cut at 10 to 15 microns. And essentially, it's going to let us see the difference between white matter and gray matter on kind of a gross scale. Except when we actually stain it, the quote white matter is actually going to be darker, and the gray matter is going to be kind of a tan color. So in this case, the white matter is actually going to be darker because our white matter contains all that myelin. So when we do the actual stain, the procedure itself reminds me a lot of elastic stains. So we're going to use an iron-based hematoxylin. Instead of using ferric chloride, we are going to use ferric ammonium sulfate. And so procedurally, we are going to put our sections into that stain, which is ferric ammonium sulfate, hematoxylin, and we're going to let that stain, and then we're going to differentiate, just like we do in an elastic, with excess mordant. So we're going to use ferric ammonium sulfate to kind of get rid of all the excess that we're going to see in the gray matter here, and we should be able to keep all of the myelin staining on the white matter. So we have that extra mordant, differentiate, and then we wash that off. And then we're going to use sodium borate, potassium ferrocyanide, and that is essentially, it's going to act a lot like our sodium thiosulfate does in our other silver stains or in our elastic stain, where it's going to get rid of some excess while also doing a little bit extra differentiating. And so when it's all said and done, you should be able to see all the tracts of myelin here as it branches out from the gray matter. And then your gray matter is just going to end up being kind of a tan. Let's see if I can get this one right. Yeah, so that's kind of your background, really. Anything that's not myelin is going to have kind of this tan background to it. And that's essentially it. So wheel stain, a good way to think of it, like I said, is a lot like an elastic stain, except you're doing it for myelin, and instead of ferric chloride, you have a ferric ammonium sulfate. For our next stain, we're going to look at Nissl Fast Blue. For this, we're going to cut our sections at 10 to 15 microns, and we're going to be demonstrating myelin sheets. For this one, I've had a lot of luck using cerebellum, just because the white gray matter or the myelated and demyelated matter is fairly pronounced, so it makes it kind of easy to differentiate on a control tissue. So when we're done with this, the gray matter, so on the outside, is actually going to be colorless, and the myelinated structures are going to be blue. So the mechanism behind this is our Luxelfast blue dye. Contains a dye that has a base attached. That base is doesn't have as much of affinity for the dye as bases in the lipoproteins in the myelin. So when it comes in contact with the myelin in the environment that we provide, then the dye gets rid of its base and it attaches to the base on the myelin, and that's how our dye stays. So in order to do this, we are going to hydrate these to 95% alcohol. So a lot of this reaction takes place in alcohol. We're going to put these slides into our Luxelfast blue overnight. So then we take those out. You're going to rinse off any excess with 95% alcohol. That's not going to differentiate them. We're going to get rid of the excess that doesn't attach to anything. And at that point, everything's going to be kind of a dark blue. And so at this point, we're going to start differentiating. So the first thing we're going to do is put them into lithium carbonate. And then we're going to move on to 70% alcohol and then rinse. And at that point, we want to check the differentiation. At some point, it's going to take away blue from everything. So at some point, you might actually see more blue in the gray matter than actually in the myelin. And that just means you got to keep going. Okay, don't stop or redo this thing because it's doing that weird. Just keep going. So if things aren't as far as you need them to be, just restart this process. So go back into lithium carbonate, 70%, rinse, and check it again. When it's at the right point, the gray matter should be completely decolorized. So it should be completely transparent. And that's actually a good point to look for. If your gray matter is transparent, then you're basically done, because the myelin is going to hold on to the blue. So when it's done, it's going to be this color, and that's going to take me forever if I do it like that. But it's going to be a really vibrant blue. And the gray matter, once again, is going to be a bit of a misnomer in this case, because the gray matter is going to be translucent, and then all of our myelinated white matter is going to be blue. Now granted, some of the white matter, if it's demyelinated, is also going to be transparent in this case. But you should end up with something that looks like this. So like I said, you might have, during differentiation, you might have blue, you might have this holding on to this blue, and it's actually seeming to be darker than your gray matter. Just keep going, because eventually this gray matter will give that up, and it'll just leave the myelinated white matter. So yeah, that's Luxelfast blue. It's fairly simple. You just gotta make sure that you're paying attention to differentiation and don't over differentiate, especially if your docs are trying to find those myelin sheaths. You might be looking for a degradation of myelin sheaths, so you don't want to make an artificial degradation when there is still myelin sheath there. But as far as your control goes, once the gray matter goes translucent, then you're done, because you want to make sure that you're keeping as much myelinated tissue as possible. Now, something that you may have noticed about the mechanisms in this chapter is a lot of them are fairly separate from each other. So a Luxelfast blue and a Chomsky don't have a lot in common in terms of mechanisms. So it's totally possible to intermix a lot of these techniques so that you can see things like myelin sheaths and neurofibrillary tangles in the same stain. So the text that I'm using covers some of those combination stains, though I am going to refrain from going over all of them, because it's essentially just do the stain that we know and then add another stain on top of it. And you just have to kind of look at the mechanisms and see which one would be disrupted by which to know which order to go in. So I would assume that if you work in some sort of neuropathology specialist laboratory, that would be an important thing to know. But for most of us, it's really not going to be all that important. I'm not going to put a bunch of time into that. So if that's something that interests you, absolutely look into that. But for the sake of this lecture, we're essentially done. That's most of our neural tissue stains that are important. And as I said, I'm really just going off the reference material for a lot of this. I've done the stains as a student. I really don't do a lot of these in practice, just because a lot of them have analogs in IHCs. So you probably won't see a lot of these done routinely in the lab, unless that's a specialty of yours. And a lot of these you're going to see actually replaced by immunohistochemical stains, which we'll get to after specials. So that was Chapter 9. Up next is Chapter 10, which is microorganisms. And I hope that everybody keeps in mind the things we talked about at the beginning of this lecture, the kind of how to go about studying now that we have a big repertoire of stains to go with. Once again, congratulations on your progress so far. It's tough material, folks. And it's not always easy. It's certainly not easy the first time you learn it, and it's not even easy later on. So congratulations to you and great work. Do just keep it up, and if you work hard on it, then you'll be able to pass your exams, and you'll start a great career in histotechnology. So as always, have a good one.